Okay, I'm gonna let somebody in the waiting room here. Okay, so the first thing we wanna do is do our uh, um, administration stuff. So we have Zoom today only, okay? On Wednesday, just go directly to Top Hat and get your Proctorio set up and start the exam at class time. After that, if you have any at all mental energy, you can start reviewing chapter 12. If you don't, go ahead, just don't worry about it until the weekend and maybe pick it up on Monday morning, okay? We're gonna have a long weekend. Well, if you have parties or something to go to. We have Halloween coming up, which is gonna be interesting in the way we're administering it. My wife and I are throwing large candy bars, but only to small kids in costumes, by the way, just so you don't know. All right, so we're going to go ahead and have our review today. I'm going to kind of pick some things, and then I can actually go through some of the, then I can also go through some of the kinds of, ways to look at things a little backwards, kind of to help you figure out if you're studying the right way, because we want to be able to answer questions in both directions. Okay, so let's see, and starting next week, we're going to do chapter 12, and that homework won't be due till November 6th. Oh, the last thing for today is that today is the last day to early vote. There are 3 locations in San Marcos from 7 a.m. to 7 p.m. for early voting. After that, you'll have to wait till November 3rd. So if you wanted to go early or think you might catch COVID over Thanksgiving and can't go, over Halloween and can't go, you might want to try to see if you can vote today. Okay, that being said, are there any questions about administration? All right, no unmuting of mics and nobody chatting. So I'm going to go ahead and start with review of chapters 1 through 11, and I'm going to go backwards. I'm going to start with chapter 11 first, and we're going to continue on until we have some people asking questions about stuff. Okay, so let me go ahead and share my screen with my okay, let me mute my watch. Okay, so the first thing I want to do is I want to talk about spectroscopy. I'm going backwards because this is the last thing we covered, and maybe you have some fresh questions in your head and that we can talk about them or look at them in the chat room too. So in spectroscopy, we have the 2 types that we were looking at. One is the, okay, I need to switch styluses. That one's just not working at all. There we go. One is using a magnetic field and radio frequency, and that's NMR, nuclear magnetic resonance. What we're looking at is the nuclei, or the odd molecular weight isotopes of the actual elements. And we have 2 types of those that we're going to work with. One of those is what we call Proton Nmr, which is the hydrogen with no neutrons in it. So it's molecular weight 1, atomic number 1. And that means it has spin. And we can test that spin using that magnetic field with radio frequencies. We also have carbon-13, which is a little known, a lesser isotope of carbon. Carbon was mostly carbon-12, but we have a 1.1% of carbon-13, which is the exact same number of protons, but it has 1 extra neutron, making its molecular mass higher. That 1 extra neutron allows us to see it in this high magnetic field when we pulse it with radio waves. Now, in carbon NMR, because the signal is so low, because there's only 1.1% of all carbon we can see, we only look for 2 things in carbon NMR. The first thing we look for is the number of different types of carbon. So we have to think about symmetry and the shift of those things. Now remember, the shift of things are consistent, whether they're, the further upfield they are consistent with what we see in proton NMR. So if it's more like a hydrocarbon, like butane or propane, then it's going to be down in the 0 to 20 range, okay? If you add an electronegative atom, like oxygen or a halogen, it shifts it up into the 40 to 60 range, okay? And if you have a carbon-carbon double bond, that's going to shift it up into the 80 to 100 range, okay? And if you have a benzene ring, that's going to be centered around 120. And then if you have a carbonyl, those are the things that are going to be shifted highest. And they start around 170 for things that are like carboxylic acids. And things over 200 are things like aldehydes and ketones. Okay, so the two things we need to play with are what kind of things are bonded to that carbon you're looking at. Are those carbons unique? So look for rings. Usually in rings that you can have 2 or 3 different types of carbons, but you'll have 2 of those carbons that are exactly the same. So look for symmetry when you're thinking about number of signals. If you have an unsymmetrical molecule, every single carbon is going to have a unique signature. Okay? So in contrast to the carbon NMR, we have proton NMR. And in proton NMR, because the proton is the major isotope, it's 99.9%, is that we get to see, number one, a very strong signal, and we have a very clean spectrum where we can look at the intensity, which is telling us the number of hydrogens of that type. We have our position, which is the same as with the carbon-13, and that depends on what's bonded to. But then we also have spin-spin coupling. And that spin-spin coupling actually tells us how many hydrogens are adjacent to that hydrogen. Okay. So number of signals is just like in carbon NMR. We're looking for unique hydrogens. So if you have 2 hydrogens on the same carbon, they're the same. And if you have hydrogens on carbons next to them, then we have to pay attention to them. But so we're looking for number of signals, which is unique. Again, symmetry plays an element here where you can have a symmetrical material like this, and you're only going to see 1 peak for those hydrogens, okay? But if you make it unsymmetrical by just adding a methylene to the thing, now we're going to see actually 3 different hydrogen signals because of that lack of symmetry. Okay, so we have that, we have that number of signals is based on the number of different types. The intensity is based on the number of hydrogens. The position is based on what's bonded near that hydrogen. So if that hydrogen is bonded to a carbon that has only carbons and hydrogens to it, they're going to be shifted very low, below 2 ppm. Okay. When we start adding things like halogens and oxygens, we're going to shift it up to around 3 to 4 ppm. When we add a double bond, that's going to shift it up to 5 to 6 ppm. When we add a benzene ring, that's going to shift it up to 7 to 8 ppm. And then the craziest of hydrogens we have are the ones that are aldehydes and carboxylic acids. And those typically show up above 10. Okay, so that's as far afield we can shift those hydrogens up. Now, the last thing is spin-spin coupling. And we got to remember our N+1 rule. Okay, so N+1. Okay, the 1 is for the hydrogens on the carbon we're talking about. Okay, there can be 1 hydrogen there, 2 hydrogens there. There can be up to 3 hydrogens there. Okay, that gives us 1 signal for all the same and all the identical or the identical type of hydrogen. Okay, the N is for the number of hydrogens within 3 bonds. Okay, so you could have, it has to be within 3 bonds. So you can have 2 hydrogens over one direction, 3 hydrogens over the next direction. That's a total of 5. So that's the total number of hydrogens within 3 bonds of these, of the signal you're talking about, which is that 1. And so if you had 5 hydrogens within 3 bonds, you have a total of 6 signals. And so we have to remember what the 1 stands for is the hydrogens that are unique, and the N are any hydrogens that are within 3 bonds of those hydrogens. And that gives us our structure for our proton NMR. Okay, questions about proton or carbon NMR? Okay. All right, well, if you have a question, go ahead and put it in the chat or go. Question. I heard a. All right, 2 people are trying to talk. Let me stop my video.
Yes, sir.
Scotty, I think his.
All right, I got 2 people. All right. All right, we're typing. Can you explain upfield and downfield? Ah, great question. Okay, so upfield and downfield, and well, somebody else is typing. We'll answer this question. So upfield is as close to 0 as you can get. So if we look at our standard, which is called tetramethylsilane, we always put that in there to show where 0 is. And so the closer you are to 0, the more like a hydrocarbon you are. The more like a hydrocarbon you are, the more upfield you are. As you add things to there, like electronegative atoms or double bonds, then you go downfield and you get to higher and higher ppm numbers. Okay? So that is upfield, downfield. Okay. And so you can think of just higher numbers is, downfield, lower numbers is upfield. All right. Still typing, Alexis? All right, I'm going to go ahead and start video again. All right. So while you're typing, I'll go ahead and talk about IR a little bit, and then I can answer your question when you have it typed. So the most important thing about IR spectroscopy is, number one, you have a no telling them the audio is messed up on your side. The audio is messed up on my side. Oh, okay, I see. Thank you. That clears everything up. Okay, great. All right, in IR, what we have is infrared spectroscopy, so it's just below visible light. And unlike NMR, where we're looking at connections and how hydrogens are connected to carbons and stuff like that, the only thing we care about is a single bond between 2 atoms. A bond between 2 atoms and the nature of that bond between 2 atoms. Okay, so when we look at IR, we're not looking for a functional group or a connection. We're looking for specific types of bonds. And we have 4 zones for those specific types of bonds. We have zone 1 right here that are all the heavy atom light atoms. So it's carbons bonded to hydrogens, oxygens bonded to hydrogens, and nitrogens bonded to hydrogens. And remember, they have each a different shape. Like OH is really broad. NH can be 1 or 2 peaks depending on how many hydrogens are there. And the carbons shift depending on what kind of hybridization we have on the hydrogens on there shift based on what kind of hybridization we have on the carbons. So our sp hydrogens are going to be way high. Our sp2 hydrogens are just above 3,000, and our sp3s are just below 3,000. And don't forget that weird peak with our aldehyde, which is about 2,700. Okay. So those are our light elements, heavy elements, and they have the highest frequency, the highest energy. Because if you can imagine, the bigger element is not going to move as much as the smaller element, and the hydrogen is so small it can move very quickly. So that's why it's a higher frequency number. Okay. The next thing we have is the tightest bonds we have are triple bonds. And so you would imagine that those would also have a higher frequency because it's a stronger bond. And we put those in our zone 2. And our zone 2 is 2,000 to 2,500. Almost nothing else shows up in that region. So usually it's very easy to see those carbon-carbon triple bonds and carbon-nitrogen triple bonds. But remember that they might not also be strong because the bonds vibrate more when you have a polar bond. Okay. I have a question. Let's see. The frequency has to do with how fast the orientation flips. These don't flip. When we have IR radiation, what happens is the light comes in and interacts with the bond. If it's the right energy for the bond to absorb it, it absorbs that energy and causes it to vibrate or stretch or twist or something like that. And so that's when we look at an IR, it's actually, we're looking at percent transmission. Because if you have 0% transmission, that means 100% of that energy got absorbed by that bond. Okay, so when you have something that absorbs very strongly, yeah, flipping is only in our nuclei in our carbon and proton NMR. And you flip them, they align in the magnetic field, and then you hit it with radio waves that flips them, and then you wait for them to relax back. And that's what we see in NMR. Okay, so IR is different because we're actually absorbing the light and converting that light into motion or heat, and we can see those bonds vibrate. So as we move from a triple bond down to a double bond, we get to a slightly longer bond, and so it's going to have a slightly higher frequency, lower frequency than the triple bonds, but a higher frequency than the double bonds. And so we have that intermediate range, 1500 to 2000. All of our carbonyls show up here, and they shift around based on what functional group it pertains to. Carboxylic acids a little bit lower, aldehydes a little bit right in the middle, ketones a little higher. They each are kind of shifted slightly, but you can tell the difference between carbonyls and other functional groups by where other frequencies are absorbed. Just because you have an absorbance in the 1700 range does not mean you have a ketone. You have looked for the other absorbances too, okay? And then below 1500, we have all of our single bonds, carbon-carbon, carbon-oxygen, carbon-nitrogen, and carbon-halogen. So the three most important ranges for helping identify our functional groups is looking at zone 1, 2, and 3. And then by adding all the different absorptions up, you should be able to pick out the functional group. So let's say you had an absorbance here, but no absorbance here and an absorbance here. Well, now you're starting to say, okay, well, I might have an alcohol or I might have a carboxylic acid, and looking at where this shifts a little bit, shifts up or down, that can tell you one thing or another. You can also see where this shifts. If you had a carboxylic acid, it's gonna be broad and lower. If you had an alcohol, it's broad and higher. So by adding the different things you do see together, you should say, oh, I definitely have an OH, I definitely have a carbonyl, but it's not a carboxylic acid because those look special. Those look different. Okay. So that's the key to IR spectroscopy. Look for the different types of bonds you have and then lay those out. And then if they make that functional group, you have a pretty good idea that that's what you have. But again, it doesn't tell you about connectivity. That's what the NMR is for. All right, questions on IR. So really, I think if you understand this chart right here and understand that they are being absorbed, and by adding the different types of bonds together, I think that this is really what I want you to understand about IR. And then in the slides, you'll see, as you go through the different functional groups in that full video, you'll see that, oh, I added this bond and this bond and this bond. That means I have an aldehyde. I added this bond, this bond, and this bond. That means I have a terminal alkyne. I added this bond and this bond and this bond, and it means I have an internal alkyne. So you have to look for what you are absorbing and then try to figure out what's happening from there. All right, questions on IR? Okay, don't be scared of the chat room. All right, so chapter 10, amines. Okay, one of the weird things about the amine chapter is we talked about basicity. Up to now, everything was pKa, okay? So now we talked about basicity. So the most important thing we need to remember about basicity is that your aliphatic amines are the strongest bases, followed by your heterocyclic bases, and then aromatic amines are the weaker of the bases in the set. Okay. Now, if you'll remember your homework, you had a problem where it had an aromatic amine. Okay. And because the aromatic amine has conjugation in it, by adding a group to that benzene ring, you can make it more or less basic by making it more or less adding more or less electron density to that lone pair. So if that lone pair on the nitrogen that is outside that benzene ring is being weakened by being pulled into the ring by having an electron withdrawing group, like a carbonyl or a nitro group, that's going to make this less basic because we have less of a lone pair. The smaller the lone pair, the less basic it becomes. And if we think about it, the aromatics, those can share with the aromatic ring. And so they're less basic than aliphatics that can't share. There's nothing for them to share. That lone pair is stuck on that nitrogen. That's why they're more basic. Okay, so we have a total of definition of 4 different types of amines. We have an aromatic amine, an aliphatic amine, okay? And those are pretty simple. But then we have a heterocyclic amine, which means the nitrogen is part of the ring. But then we have an aromatic heterocyclic amine, the most specific of the set, okay? So that means the amine actually has at least 1, if not 2 electrons contributing to the aromaticity, and it's still in the ring. So it's the most specific type of amine we have. Aliphatic, heterocyclic aliphatic, aromatic, heterocyclic aromatic. Those are the 4 types of amines we have. Questions on amines? Okay. That leads us to our benzene ring reactions. Okay. Chapter 9. Okay. So remember that benzene ring derivatives have special names. Know these ones in this chart. They are going to be very helpful for helping you do that. Okay. So know that there is a different nomenclature system for benzene rings. In fact, when you have substituents, if it's in the 1-2 position right next to each other, it's ortho, meta, and para. Know the difference between those. And know which things are directing and which things are activating or deactivating. Ortho-para direction involves a lone pair or a non-polar bond. Meta direction and deactivation involves something with a partially positive charge, okay, or a positive charge. Look at this chart, you will see that time and time again, okay? Now, we have 1 mechanism. That's great. Only 1 mechanism for our chapter 9. Our chapter 9 has 1 mechanism. It's called electrophilic aromatic substitution, okay? Which means we have to have something with a positive charge to start the reaction. That's always the first step, is generation of that positive charge. Most of the time, we're generating that positive charge with a Lewis acid. Ferric chloride, ferric bromide, aluminum chloride, or a strong acid like sulfuric or nitric. We have a Lewis acid helping us generate a positive charge. Okay. Second step is the reaction where the benzene ring is reaching out with its electrons and grabbing a hold of that electrophile. Okay. Now, that breaks aromaticity, but it still has conjugation. So the more you can spread that positive charge out over that ring, the more stable it will be. That's why ortho and para directors, because they can sometimes stabilize, have a resonance structure off of the ring because of lone pairs, that makes those reactions, number 1, activated, and number 2, more stable and faster. The last step is the same in all of them. They lose a proton to re-aromatize the ring. And remember, the driving force for aromaticity is it saves energy to re-aromatize. So we rarely see just addition reactions on benzene rings unless you're doing something crazy like a hydrogenation where you're trying to get rid of the benzene ring altogether. Everything else is going to be this electrophilic aromatic substitution. Questions on benzene rings? All right, type feverishly in the chat, if you will, please. Okay, so that being said, we can do a lot of different reactions here. We can add chlorine to the ring by adding ferric chloride, our Lewis acid catalyst. We can add a nitro to the ring by using sulfuric acid as our Lewis acid catalyst. We can sulfonate the ring by adding sulfuric acid with SO2, generating a sulfur cation, a sulfur positive charge. In alkylation and acylation, we have to use a different Lewis acid, aluminum chloride, and that's going to create a positive charge on carbon. In alkylation, the problem is when you create that carbocation, if it's not the most stable carbocation, it will rearrange, so you can get weird products. However, with the acylation, because you have that carbonyl there, the positive charge stays on that carbon. And if it doesn't move around, and therefore you know you're going to get a ketone, you're always going to get a ketone from the acylation, even though it's the same mechanism and same catalyst. Let's see, when identifying electrophiles in an aromatic nitration, you are using the mechanisms to identify them, or do you use another route? Okay, the electrophile is always the thing with the positive charge or possibly positive charge, right? Because it's looking for electrons. So the first step always is generation of that electrophile. Okay, now your benzene ring is now acting as the nucleophile. So, and that's true for all of these reactions. Okay, so does that help? It's the same mechanism for every single one of these reactions. All right, great. All right, so that's benzene. Okay, so that brings us up to chapter 8. Now, chapter 8, we learned a little bit about alcohols. Okay, we learned that alcohols come in different types. There's primary, secondary, and tertiary. We learned about hydrogen bonding. Okay, hydrogen bonding has to do with the idea that the oxygen and hydrogen have a very polar bond. Oxygen has 2 lone pairs on it, which means this hydrogen can have a weak interaction with a lone pair on a neighboring compound. We call that hydrogen bonding. Alcohols tend to be and carboxylic acids tend to be the ones that hydrogen bond the strongest. Okay. Now, once we have alcohols on ring, we have a couple different things we can do. First of all, the first thing we can do is what we call a dehydration. When we dehydrate an alcohol, we end up usually making a double bond. A dehydration means we move an OH on the 1 carbon and the H on the carbon next to it, or the beta carbon. So you're eliminating an entire molecule of water, hence the word dehydration. So this is very difficult in primary alcohols and requires a lot of heat and a lot of strong acid. Secondary alcohols, because it's more easy to form a partially positive carbon on that secondary alcohol, it happens at a lower temperature. Excuse me. And for tertiaries, because it's really easy to form a carbocation with the tertiaries, it happens really easily. Okay. When you do dehydrations of alcohols, always follow Zaitse's rule. The more substituted double bond is the more stable product. Okay. Now, if we don't want to dehydrate and make a double bond, we can do other things with alcohols. The first thing we can do is we can oxidize a primary alcohol to a carboxylic acid with any strong oxidizer. However, you have an opportunity, because there's a hydrogen on that primary alcohol carbon, to stop at the aldehyde, but you must use pyridinium chlorochromate, the PCC. And a typical solvent for that is CH2Cl2. It does not participate in the reaction. It is just a solvent. Okay. So if you want to stop at an aldehyde, you have to use PCC. If you want to go to a carboxylic acid, use any oxidant you want. Okay. Secondaries can take any oxidant, including PCC, and turn them into ketones. So again, you always get a ketone, and you can use any oxidant to do so. Okay. Tertiary alcohols don't react. There are no hydrogens on the carbon with the OH on it. If there are no hydrogens on that carbon, it cannot oxidize. Okay. So then the cool thing is another way to make alcohols is to do what we call a ring opening reaction. Now, because that's a small ring, it's got 3 members in that ring and they want to be 190 degrees, 109 degrees, and they're at 60 degrees here, there's a lot of ring strain. So any nucleophile that comes along will open that ring, giving you an alcohol on one carbon, and the nucleophile is going to make a new sigma bond on that other thing. You can attack it with any nucleophile, a weak nucleophile. Notice we have, in this case here, a neutral amine as a nucleophile. That lone pair just, boom, opens up the ring. You get an alcohol and an amine group. You hit it with water, you get 2 alcohols. You hit it with any other nucleophile, you'll get the nucleophile with a new sigma bond and the alcohol on the 1 carbon over. Okay? So those are all the reactions we learned about alcohols. We'll learn some more when we talk about aldehydes and ketones, but these are the ones we need to know for now. Okay. All right. Don't forget to ask questions in the chat there. I keep looking. Okay. So let's talk about nucleophiles a little more. Okay. We have to compare every different reaction we have what we call the substrate, which is the alkyl halide. Okay. So we need to know something about the substrate. So is it a primary, secondary, tertiary, or methyl? Okay. So that's the first piece of the puzzle when we're talking about SN1, SN2, E1, E2. The second piece of the puzzle is is the nucleophile strong or weak? Okay. Remember, there's a table for making strong nucleophiles. Those are charged species that have oxygen on them or nitrogen on them. And then as they go, and things like iodine and bromine, great nucleophiles. Okay. Then you have things that are maybe not as good at nucleophiles, like chlorine and fluorine. And then you have things that are like acetate, things that have a shared charge. Those become weaker and weaker. Okay, so we need to figure out whether it's a strong nucleophile or a weak nucleophile, but we're not done yet. The last piece of the puzzle is, do we have a strong base or a weak base? Okay, so when we think about things like alkoxide, or like in this case right here, we have methoxide. So any salt of an alcohol or hydroxide ion itself, those are all strong bases. Okay, and we have a choice between an unhindered base or a hindered base. So if you see T-butoxide, think hindered base. Almost all the other ones are what we call unhindered bases. Okay, so type of alkyl halide. Number 1, is it a good nucleophile or poor nucleophile? Number 2, is it a strong base or a weak base? Okay. Once we've identified all 3 of those things, then that makes figuring out what the product is easier, because if we have poor nucleophiles, it's not going to act as a very strong base. It's not going to act as a very good nucleophile. It must wait for a carbocation to form. And the 2 reactions we have that form carbocations are SN1 and E1. Unimolecular reaction means 1, means carbocation. So that's the only way we're going to get them to react. And only secondaries and tertiaries can form carbocations at regular laboratory conditions. So if you have a tertiary alkyl halide refluxing in water, it's going to be a competition between SN1 and E1 because of the requirement to form a carbocation. Now, let's say you don't have a base, you have some other nucleophile, right? Then almost always you're going to do the substitution as the primary reaction, okay? Until you get to the tertiary right here, because of sterics, there's going to be that formation of that carbocation. Whenever you form that carbocation, it's always going to be a little bit of both. But again, if we have a decent nucleophile, substitution might be a little bigger. Okay. Once we get to our strong base, our first strong base, okay, In a methyl group or a primary, we can get substitution because they are also a good nucleophile, but a strong base. However, for once you start getting it steric demanded or a secondary or tertiary, it always goes E2, elimination of a beta hydrogen to form the more stable double bond. Okay. Once you get to a hindered base, it rarely does a substitution reaction, except on a methyl group. The rest of the time, it's elimination. Okay. So notice there's only one thing here that actually will go 4 different mechanisms. It's a secondary alkyl halide, but it's very distinct. Poor nucleophile, poor base equals SN1 EY. Good nucleophile, poor base, SN2. Strong base, E2. So that's the one where you have a choice, but when all you have to do is look at the base strength versus the nucleophilic strength to determine whether it's forming a carbocation, not forming a carbocation and substituting, or eliminating. Okay, when talking about hindered or unhindered, yes, it's how many things are close to your oxygen with your charge. So in the case of something like this, this would be the ethanol, the salt of ethanol, which would have, you know, a counterbalancing ion here. And we consider that an unhindered base, okay? Now, we can even go up to this salt of isopropanol, and that is borderline. See how you have that next methyl group there giving a little bit of bulk to it? However, this is still what we would consider an unhindered base, okay? However, if you go to one more methyl group, that is a hindered base. The other thing that can make a base hindered is if you had even a secondary like this with 2 different ethyl groups on here, that now starting to look like a hindered base. Anything above an isopropyl group is going to be a hindered base. Okay, E2 elimination of what? Okay, E2 elimination is a bimolecular elimination reaction, meaning we have the loss of the halide on one carbon, and then one carbon over the loss of a hydrogen. So basically you're losing like HBr or HCl, you're losing an acid to get to that E2 elimination, okay? And so the carbon with the leaving group on it is called the alpha carbon. The carbon one carbon over with hydrogens on it is the beta carbon, and the hydrogens on that carbon are called beta hydrogens, okay? All right, so let's talk about the different kinds of nucleophiles we have. Depending on what you're attacking with, tells you what functional group you're making, right? If you attack with hydroxide, you're gonna make an alcohol. If you attack with an alkoxide or the salt of an alcohol, you're gonna make an ether. A sulfur group is gonna make a thiol or a sulfide. Iodine is gonna make a different alkyl halide. Amines are gonna make ammonium salts. And if you lose that proton, it'll be a regular amine. If you attack with water or methanol, notice the things when you're attacking with a neutral species, the intermediate actually is a protonated species that if you lose that proton, it becomes that normal functional group. So that being said, by the way, I'm going to my allergist tomorrow and my gastroenterologist on Thursday to see if they can cure my cough. So sorry, I thought I'd update you on that one. Okay. Notice the trends in our nucleophiles, okay? If it has a charge and it's something that can, like an oxygen negative charge, a sulfur negative charge, or bromine or iodine, we call those good nucleophiles, okay? Notice they're also, if we looked at them, so we also, some of these are bases too. We also have the hydroxide, the methoxide, and the alkoxide are actually bases. And you look to the pKa of the conjugate acid to determine which are which. If it was a very weak conjugate acid, that makes it a strong base. If it's a very strong conjugate acid like HI, it's a weak base. So don't forget, that's how you tell the difference between strong base and weak base, or strong in this system, okay? So next down are the smaller charged species, chlorine, fluorine, the shared charged species, the carboxylic acid, deprotonated carboxylic acids, and the neutral sulfur and nitrogen compounds. So those are good. Even though they're neutral, they are good nucleophiles, or moderate nucleophiles, sorry. And then the last set is neutral water, neutral alcohols, and neutral carboxylic acids. Those are poor nucleophiles because they're not charged. They're relying 100% on the lone pairs to do the work. Okay. And so when you have poor nucleophiles like these last three here, you got to wait around for that carbocation to make it react. Okay. So that is a summary of SN1, SN2, E1, E2. Okay. So look for, when you're trying to decide between them, what kind of halide do I have? Primary, secondary, tertiary, methyl. Is it a good nucleophile or a poor nucleophile? Is it a good base? Is it a poor base? And then from that, you can make a logical argument to tell you what your products are going to be based on this table here. Strong hindered base, almost always E2. If it's small enough, it can do some substitutions. If it's a good nucleophile but poor base, it's not going to do elimination. Or at least I'll have to wait around for a carbocation to do it. And if it's a weak nucleophile and weak base, almost nothing happens until you form a carbocation that might do something eventually. But it's really, really slow. Okay. So that's chapter 7. Okay. Chapter 6 was stereochemistry. Okay. Now, remember our nomenclature in stereochemistry. If we have a mirror image of compounds that are non-superimposable, those are enantiomers, okay? And one of them has to be named R, and one of them has to be named S, okay? And we use our nomenclature rules to determine those, okay? Okay, so those are enantiomers, okay? If you have more than one stereocenter, you can then have a new set of compounds. Now, if you had two stereocenters, you're going to have one pair of enantiomers that are non-superimposable, mirror images. And then you're going to have another pair of enantiomers that are mirror images and non-superimposable, but don't look like the other set, okay? So we have two pairs of enantiomers, but the set of them are the diastereomers. Okay. Now, remember the one thing that kills chirality in a system, a mirror plane, okay? So if you only had one stereocenter, but you had chirality in your system, if you have a mirror plane in that system, it will kill your chirality. For example, if you have a methyl group on a cyclohexane, if you can draw a mirror plane in the middle of that cyclohexane and it looks the same on both sides, it is not chiral. And when we have two or more of our stereocenters in a system, and we have a mirror plane in one of the compounds but not the other, that one compound with the mirror plane is a meso compound, still a diastereomer, but we only have one of those compounds and it is no longer chiral. Okay, so remember how to do R and S, right? R is clockwise, S is counterclockwise, and priority is the same we use in both alkenes and for chiral compounds. Right. Okay, no new comments in the chat. Any comments on stereochemistry? Stereochemistry is one of those things that you got to practice on it. That's why we did the activity in class. Okay, so chapter 5 is talking, we have to talk about mechanisms, okay? So mechanisms is just kind of how we describe the thing and letting us know that things happen at the same time or concerted. So if it all happens in one step, we form a bond and break a bond at the same time, we have one hump in our coordinate diagram, and we only have a transition state, and the energy associated with that is called our activation energy. If we have a two-step reaction like the formation of an intermediate like a carbocation, we have two humps in our reaction diagram, and we have two different activation energies. Okay, the one to make the intermediate and the one to react to the intermediate. Okay, so it's easy to tell whether a thing is one or two steps based on the coordinate diagram, and if you have a reaction drawn where intermediate then reacts, you know it's a two-step reaction. We learned that there is 5 patterns to look for in a mechanism. We can add a proton. So like in the dehydration of alcohols, we add a proton to make the OH a better leaving group. Okay. We can take a proton away. We can deprotonate something to make it charged. We can have an electrophile and a nucleophile react. Partially positive, partially negative, react to form a new sigma bond. Okay. Or we can break a bond. Okay. Typically, when we break that bond, we form a carbocation. Okay. And if we form that ion or that semi-stable ion, then can it rearrange? Can it be more stable? So if we formed a secondary carbocation and it can rearrange to a tertiary carbocation, it will. Those are the 5 patterns that we have available to us as mechanisms. Notice if we go back to the aromatic rings, right? The first thing we do is we have a reaction of an electrophile with a nucleophile to create a positive charge. Step 1. We have the reaction of an electrophile with a nucleophile, step 2, and loss of a proton, step 3. So we see those same patterns in all of our mechanisms. Know why tertiary carbocations are more stable. Okay, tertiaries are more stable than secondaries, more stable than primaries, which makes methyl and primary very hard to make. So we can only do those under special conditions. Okay, so secondary and tertiary are low enough energy barrier, we can make them routinely in the lab. But if a secondary can become a tertiary by transferring a methyl group with its electrons or a hydrogen with its electrons, 1 carbon over, it will. But only to go from secondary to tertiary. Okay. All right. So also in chapter 5, now that we've learned mechanisms, we learned what we can do to alkenes. Okay, remember an alkene is a double bond. It's electron rich. All right. So it tends to be our nucleophile. And so what we do is we found that we can add stuff across there. So we had a whole bunch of, quote, addition reactions. We can add acid across a double bond. Okay. We can add water across a double bond. But what's the rule when you add acid across a double bond or water across a double bond? We have a rule to where the hydrogen goes, right? The hydrogen goes on the carbon with the most hydrogens. Okay, it always goes on the carbon with the most hydrogens because of that intermediate partially positive carbon charged state. Okay, so there's that. And then we can also add a halogen across the double bond. But remember, that's a slightly different mechanism. In the one mechanism, you're forming a new bond, giving a partially positive, partially negative zone, and then you get addition here. In the addition of a halogen, you put one of them on one side, giving you a 3-membered ring, and then the other one has to come on the other side. Okay, so it has to come from the other side. And in hydrogenation, both hydrogens go on the same side. Okay. In that set, we also learned about the acidity of different ions. sp3 hybridized anion is the strongest base, weakest acid. sp2 is a little more stable and therefore a little more acidic. sp is even more acidic, and hydroxide is the least acidic of that set. I mean, the water is the least acidic of that set. Okay. That general trend of pKa's and Ka's just keeps coming up. It came back in amines. It came back in, it'll come back in a couple more reactions, a couple more chapters as well. This leads us to nomenclature, okay? Prefix, infix, suffix, okay? Don't forget the suffix is telling us what the functional group is. The infix is telling us whether we have single bond, at least one double bond, or at least one triple bond, okay? Then the prefix is how many carbons we have in our longest chain, okay? And when we change our names, we change the end of the reaction. Alcohols or alls, aldehydes, ketones, etc. Okay? So, but when we look at our alkyl halides and when we look at our carbocations, we have to remember that we have degrees of carbon. And so your degree of carbon is how many other carbons are attached to that degree. We have primaries only have 1, secondaries have 2, tertiaries have 3, quaternaries have 4, okay? Which means we can only have primary, secondary, and tertiary alkyl halides. We can only have primary, secondary, and tertiary alcohols. Because if you attach that 4th carbon on there, it removes the functional group. Okay. Will you be posting this lecture to YouTube? Correct. Yes, I will. And this review is also posted on Canvas. Okay. All right. Know our primary, secondary, and tertiary and methyls. Follow that trend. Our amines are backwards. Our amines are always about how many carbons are attached to the nitrogen. So just remember that it's always the number of carbons attached to the nitrogen for amines, and you'll get that right. So that rule also follows for amides. It's all about how many things are attached to the nitrogen. And in an amide, the first thing has to be a carbonyl group. The second one can be another type of carbon. The third one can be another type of carbon. But amines and amides are backwards from the alcohols and carbons. Okay. So we've hit nomenclature really, really hard. Okay. I want to go over priority one more time. If you can differentiate an RNS or a double bond, one half of the double bond versus the other half of the double bond, by atomic number, you're done. Don't go, complicating things. However, if you go over one and you cannot tell the difference, carbon, 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 hydrogen, you're done on this side. Carbon, carbon, what's next? Okay, that's rule 2. And if you can differentiate on that next bond over, you're done. If you can't, or if you have a double or triple bond, you have to use rule 3. Each bond counts as bonded to that group. So a carbonyl counts as a carbon bonded to an oxygen bonded to an oxygen. So it's bonded to 2 different oxygens. So that's rule 3. So the priority rules are the same for RNS and E and Z. Let's see, know your common functional group, your common substituent names, isopropyl, butyl, isobutyl, sec-butyl, tert-butyl. Our different classes of hydrocarbons. We've now explored each of these classes of hydrocarbons. We've done alkanes. They don't do much but burn. Alkenes, we do a lot of addition reactions on them. And we can take functionalized alkanes like alcohols and alkyl halides and turn them into double bonds. Our alkynes can be deprotonated, and our arenes do a bunch of those reactions, but all the same mechanism. Okay. Lewis acid and base. You have about 7 of these things you need to kind of have rack and stacked in your head about where they show up on the pKa scale. Okay. Notice we've hit this on almost every chapter after chapter 2 at least once, because it drives a lot of our reactions. Okay. The most important definition to remember is Lewis acid, Lewis base. Lewis acids accept electrons. So you think of those as Lewis acids as partially positive or having a positive charge. Lewis bases have a lone pair to donate. Okay. And that allows us to use the same definition for acid base that we use for Bronsted-Lowry. Okay. Except in this case, we're actually transferring a hydrogen. Lewis acid, you don't have to transfer hydrogen. It's a broader term. In Bronsted-Lowry, you don't have to have water, but you do transfer a proton. And that gave rise to our acid-base, conjugate acid, conjugate base. Don't forget, those are kind of important for what we're doing. And then Arrhenius has to happen in water. So it's the least important for us in organic chemistry. Bronsted-Lowry tells us about acid and conjugate acid, base, and conjugate base. But Lewis acid base describes all of these reactions. Oh, and the other thing is Lewis acids are electrophiles. Lewis bases are nucleophiles. Okay, write that down. That's important. Okay, so that's why acid and base is brought up so early in the thing, because we use it again and again and again. And if you can if you remember that a Lewis acid is an electrophile and a Lewis base is a nucleophile, we're going to use it for every other different reaction we do. Okay, had to let somebody in the from the waiting room. Which brings us to our first chapter. Okay, our first chapter has the 3 things you need to know about that. Valence electrons do all the bonding. Valence electrons do all the bonding. So a sigma bond has 2 electrons, and those are valence electrons. A pi bond has a sigma bond, a double bond has a sigma bond with 2 electrons and a pi bond with 2 electrons. 4 electrons total. An alkyne has a sigma bond with 2 electrons and 2 bi bonds with 2 electrons each for a total of 6 electrons. Okay, and guess what? By being able to go from a just sigma bonds to a pi bond to 2 bi bonds changes your hybridization. And when you change hybridization, you change shape. Make sure you know the shapes of the 3 different types of hybridizations we go through. And know that carbon isn't the only one that hybridizes. Our oxygen is hybridized the same way, sp3 hybridized. Our nitrogen is sp3 hybridized, unless we have it in an amine or an amide or a carbonyl, where those are now those have changed hybridization. And then of course we have our 7 common functional groups. We've gone up to, let's see, we've done a little bit of aldehydes because we made aldehydes and ketones from alcohols. We had amines and hydroxides that we made by nucleophilic substitution. We introduced carboxylic acids, but we have a whole chapter on that we'll talk about. And then the carboxylate and the ester and the amide are derivatives of carboxylic acids. And we'll talk about more about that later. But these are our 7 common functional groups we'll be using throughout the rest of the semester. Okay, questions on chapter 1? Okay, I don't see any mics coming up. I don't see anybody chatting. Okay, well, if you have somewhere to run off to, go ahead and run off. If you don't and you want to ask a question, stay behind and I'll see if we can't get my miking system to work so that you can ask your question, okay? So, but that is everything you need to know for our next exam. We should review the homework and review mostly correct. The homework is going to give you the style of questions asked. The goal slides give you the top 3 things in each chapter. And the review gives you an overall of kind of how they all fit together. See how acid was in multiple things, nucleophile was in multiple things, hybridization was in multiple chapters. Notice that common theme. So those are kind of important topics. Okay, does that answer your question? All right. So, but definitely review the homework. The homework has that style of question I'll be asking. The goals have the top things that you need to understand, but the full slides have the details. So if you're a broad stroke person, the goals will help you a lot of way. If you need to know the details to really get down into I want to get the 100% on the exam, the longer slides are the ones with all those extra details. Okay, so question?
I have a question about the homework in the benzenes.
Yes.
Question H20.13. Could you explain again why image 2 isn't aromatic?
Okay, let me go ahead and stop sharing here. And then what I'm going to do is I'm also going to stop recording, because when I stop recording, it'll be easier for you to talk for some reason. Okay.